Welcome to the PetroSkills PetroAcademy skill module covering reservoir fluid displacement at the fundamental competency level. In the vast majority of wells that have been drilled all over the world since the late 1860s for the purpose of producing hydrocarbons, the target fluid, such as oil or gas, has eventually been replaced by a less desirable fluid, such as gas or water. This has the effect of both decreasing revenue and increasing costs, causing the profitability of wells, reservoirs, and fields to suffer. Therefore, it is critical for the reservoir engineer to understand how one fluid displaces another in the reservoir. This phenomenon was first examined in the Reservoir Rock Properties Fundamentals module at a microscopic level. In this module, we take the ideas presented there and apply them at a larger scale to predict when water will break through in an oil well, for example. We are also going to take some ideas from an ancient text on strategy, The Art of War, and discuss how fluid displacement can increase hydrocarbon recovery if carefully engineered. Sometimes artists make interesting pictures by filling the tiny space between two very close glass plates with a colored liquid, and then injecting a second liquid of a different color to displace the first one. This qualifies as art, as every time the process is repeated, a different, highly complex pattern emerges. To a reservoir engineer, however, these images represent millions and millions of today's dollars, spent nearly 100 years ago to try and understand the physics of one fluid displacing another in porous media. The two glass plates were used to create a physical analog for Darcy's law in a perfectly homogeneous reservoir. We still don't have a deterministic mathematical model to accurately predict the complex patterns shown here, but we have managed at least to create some reasonably reliable models to predict what should happen in our reservoirs when one fluid displaces another. Here is an example of a Hellashaw cell being used to study flow into a partially penetrating well, where each of the red lines is a trail of ink recording the movement of the fluid from the left to the right. Can you see the analog? This section will cover the following learning objectives. Calculate the breakthrough time for an oil well using a collection of different methods. Explain how rock and fluid properties, as well as reservoir geometry, affect the breakthrough time. Model the flow of two fluids concurrently through the same rock volume. Recognize how flow rates and pressure drops vary under two-phase flow. Calculate recovery factors for reservoirs experiencing two-phase flow as a function of time. Use correlations to estimate aerial and vertical sweep efficiency. Calculate water influx into hydrocarbon reservoirs using a variety of aquifer models. And recognize the strengths and weaknesses of popular aquifer models. And this is the order in which we will cover these objectives. The first section is breakthrough time, where we will discuss the time it takes to see the second fluid. The next section is rates and pressures. In this section, we look at how the transport equations change to accommodate the second fluid. In the third section, recovery efficiencies, we determine how much of the first fluid we can recover. And in the last section, aquifers, we look at how the water from the aquifer invades the hydrocarbon reservoir.